start? Yeah. Yep. First of all, good morning. I'm glad again to give you a course on partial differential equations this time. And I'm also glad to see a lot of faces that I already met earlier at conferences or at workshops. And it's also nice to see that in this group we also have already students that followed earlier a course on partial differential equations or on perturbation methods or on dynamics that now are actually also PhD students. Yeah, Aditya, Diana, Eric is a former PhD student of Theo, but is also frequently visiting us in Delft. Yeah, and Koos, I think he will become soon a PhD student. Yeah, and it's interesting to see that there are good developments in that sense. Yeah, and it's very pleasant to see that, well, Theo, for instance, was a PhD student in Utrecht, and Dharma Bijoyo, who organized the previous workshop, was a PhD student in Delft. Yeah, and now they also have students, and those students also become PhD students in Indonesia or in Europe. Yeah, and you see it's spreading. Yeah, and the level becomes higher and higher. And that's actually the goal of the workshop that we are giving, to raise the level in mathematics. And you will see that in this group there will be different levels. Yeah, some of you have already a doctorate degree, some of you are PhD students, some of you are master students, some of you are still bachelor students. But what we try to do is start on elementary level, and then we go deeper and deeper. And if you are really smart, then you will grasp the ideas. And also we will give you exercises of different levels. So there will be exercises that we expect that you can make. There are more difficult exercises, and there are also exercises of which we think that most of you or none of you is able to solve directly. Yeah, we also did that the previous time in Palembang. Yeah, then we gave a lot of exercises. And then at the end we told you also how to tackle the more difficult problems. Yeah, and then if you remember, those people that were last time in Palembang, yeah, it's really, you have to think deep, but the solution is usually, if you know the solution, it's trivial. Yeah? And that's the nasty thing in mathematics. If you know the solution, it's trivial, but if you don't know, it's not trivial. Yeah? And that's what we try to bring over. Try to think deep and try to think structured, and then you finally will find a solution. But you need a lot of experience. Yeah? And to get experience is making exercises, studying, and doing things like that. Also, what we will ask you to do, you don't have to do that, but if you wish, you can hand in your CV, yeah, a short CV, and on that CV you can write down what you did, what type of bachelor course, master course, and what you want to do in the future. And then the third week, so over 2 weeks, so this week we will have a workshop, then there is a conference, and then again we have a workshop with some research exercises. Then in that week we will discuss your CV and also we look at how you progress during the course. And for a lot of you, the English is usually not good enough to do research. Yeah, because you have to publish papers in English. And that advice we are going also to give you. So if you wish, you can hand in the CVs to Fajar or to me. And then we will discuss with you in the last week. Because then we have a workshop with research exercises. And perhaps I already told you how we will set it up. We have about 7 or 8 small research projects. And you're supposed to work within a group of 3 to 4 students on that problem. And Ferdinand, Theo, Fajar and I will walk around and help you in trying to find solutions. But it's actually the group that is deciding in what direction you're going to do the research. And the research ranges from all kinds of applications. You have to make a mathematical model, you have to make an analysis, so you have different choices. Yeah? And then you have to present the results of the group on Thursday. Yeah? And each group has about half an hour of presenting the results. So you should subdivide the presentation into 3 or 4 parts where everyone can give a short presentation. And after the presentation, there will be a group discussion about what you did and the results that you obtained. Yeah, but all the research problems are coming from research problems that we are doing now in other research programs. Yeah, so there are small parts out of that, but they are completely related to what we are doing here. Yeah, so it has to do with PDEs, it has to do with ODEs, it has to do with perturbation methods. Yeah, so the whole thing will come across. Okay, today I would like to start by telling you something about Green's functions. Who knows already something about Green's functions? Green's functions, you know? Yeah, you know? Yeah, you know. Okay, but the others. Did you hear of Green's functions to find integral representations of solutions? Yeah, most of you did not. Yeah. Well, what's the goal? We would like to solve ODEs and PDEs, and we would like to have integral representations of the solution. Yeah. What you saw, and I looked at your program so far that you followed. Most of you did something on PDEs. Yeah. And you learned the method of separation of variables. Yeah? Is that true for everyone in the room? You know the method of separation of variables? Yeah? Okay. But to apply the method of separation of variables, you only use a bounded interval. Yeah? It's usually a bounded interval. If you want to know the solution on an unbounded interval, then you cannot use separation of variables. And then a way to tackle that problem is to use Green's functions. And the coming week I'm going to explain you how to do that for PDEs on unbounded domains. Yeah. Why is it important? For several reasons. You find integral representations for solutions of linear problems. And to find a Green's function is not trivial, so we have to do something about Fourier transform methods, and we have to do something about Laplace transform methods. Yeah, so that's also will be introduced during this week. And what's also important, if you know how to get an integral representation for your solution, it also gives you a way to tackle later weakly nonlinear problems. Yeah, because you always are perturbing from a linear problem, so you have to know the solution of the linear problem. But I will give you also some nice difficult problems in determining Green's function. Yeah? So for those of you that are already familiar with Green's functions, I will for sure give you a problem that will take at least a week for you to think about how to solve it. Yeah? And that's nicely because I will give the exercises on Saturday. Yeah, most of the exercises on Saturday, then there is a conference for about a week, and then we will see you back on Friday. So you have a few days to think about how to tackle those problems. Yeah? Okay, is this clear so far? Yeah? Okay, so now we're going back to what you probably saw. And for those of you that have already the PDF of the book, we are going to look at chapter 9 in the book of Richard Habermas. And I completely forgot to tell you who I am actually. Yeah, I'm writing down now a name and I think, oh well, I should tell something also myself. My name is Pim van Horssen, and I'm working already for a very, very long time at the Delft University of Technology. I'm for about 25 years deputy head of the department, and I'm teaching courses on partial differential equations and on nonlinear differential equations. And I'm also supervising bachelor students, master students, and PhD students. Up to now, 16 PhD students defended their thesis under my supervision. And I'm writing regularly journal papers on all kinds of applications where we have vibrations in elastic structures. So vibrating bridges, cables, elevator cables, all kinds of vibrations we are studying. And from a mathematical point of view, I'm always interested in developing methods to tackle those problems. So that's the reason why I'm also interested in those type of methods. Okay, that's about me. And now I would like to continue with what we're doing. We're going to look at chapter 9, and chapter 9 in the book of Richard Habermas is about Green's functions. And if you look careful, then in section 9.1 and in section 9.2. He gives a motivation why we should study those problems. And let's start for a moment with a very simple problem. Do you know this equation? That is the heat equation. Yeah? And if I give you that problem on a bounded interval, and let's assume that we have boundary conditions like this, then we have what we call temperature 0 on the boundary, we have Dirichlet boundary conditions. The equation is second order in space, so we need two boundary conditions. It's first order in time t, so we need one initial condition, and then we have, let's say, a complete problem. And that's the problem that, if you follow the course of partial differential equation, that's more or less the first partial differential equation that you ever see. Yeah, the heat equation. I'm not going to derive that because we did that earlier in our workshop, and we assume that you know that, and you know how to tackle this problem by the method of separation of variables. Yeah, so what you're going to do, separation of variables, then you're going to look for solutions in the form x of x times t of t. Then you separate the solution. You substitute that solution into your PDE and into your boundary conditions. And if you do that, then you will find x times t prime is equal to k times x double prime times t. That's if you substitute it into your PDE. And if you substitute it into your boundary conditions, you will get x0 times t of t is equal to 0 and x pi t of t is equal to 0. And so if you substitute your solution into the homogeneous PDE and in the homogeneous boundary conditions, that's important, your equation should be homogeneous, then you can divide here by x of x times t of t to obtain the following equations. T prime over t times k is equal to x double prime over x. And so you divide by a non-trivial solution. And now you have on one side a function of t and on the other side a function of x. Time x and space coordinate x are independent, so that means that here I have a function of t, here I have a function of x, and those can only be equal to each other if this is equal to a constant. Yeah? And that constant is usually denoted by minus lambda. Why the minus sign? That's only for convenience in your computations. If you look at your boundary conditions, you're looking for a non-trivial solution x of x times t of t, then it follows that since t of t is not equal to 0, that x0 is x pi is equal to 0. And now you have the following problem for your function x of x, namely x double dot is equal to minus lambda x, x0 is x pi is equal to 0, and you got an eigenvalue problem. Yeah, that's all what you know already. I assume that you know this. Who does not know this? Please raise fingers if you don't know this. Okay, so you all know this. So what you now have is an eigenvalue problem. And in that eigenvalue problem you have to determine lambda values. And then we have three theorems. And the three theorems can be formulated very simple. Theorem 1 states, if you have classical boundary conditions, so if you have boundary conditions like Dirichlet or Neumann or Robin, then we know that the eigenvalues of your problem are real, and you know that the eigenvalues are larger than or equal to 0. Yeah? So for classical boundary conditions, We know this. What do we know further? We will find lots of values of lambda that are satisfying this, and the other theorem stating the eigenfunctions x and x are orthogonal. And that's an important property. Yeah, so if you have an eigenvalue problem like this, and you might have here other boundary conditions of Neumann type, that means that the derivatives are zero on the boundary, or you have Robin type, that means that the derivative is related to the function itself, then we know that all the eigenvalues are non-negative and the eigenfunctions are orthogonal. And how do we solve that? Well, how do we find those lambda values? Look at this problem. What is the solution for this problem? X of x is a constant 1 times cosine square root of lambda times x plus another constant c2 times the sine of the square root of lambda times x. Because we know that lambda is larger than or equal to 0. And this is true for lambda positive, and x of x is just c1 times x plus c2 if lambda is equal to 0. Yeah, so we wrote down all the solutions for our differential equation. And then in the next step, what you're doing in the method of separation of variables is try to determine what your lambda values are. So you have to satisfy your boundary conditions. So let's do that. Then we have x0 is 0. That implies that c1 cosine 0 plus c2 sine 0 is equal to 0. And that implies that c1 is equal to 0. Then the other condition states that x pi is equal to 0. And that implies, using already the fact that c1 is 0, that c2 times sine square root of lambda times pi should be equal to 0. What are the values for square root of lambda to satisfy this? Yeah, we want to solve this. We have to solve this. If c2 is 0, then because c1 is already 0, then we only have the trivial solution, so this is not an interesting solution, so we skip that. And then we have to solve this. Can you tell me what values of lambda are satisfying that? Sine the square root of lambda pi is equal to 0. What are the values of lambda?
Yes.
Is this the correct answer? With n. This? Is that the correct answer? Who says this is not the correct answer? Can it be negative? No. N cannot be negative, so, and n can also be not 0 because we are looking here for lambda positive. So we should have here z plus. So this is valid for n is 1, 2, 3, etc. So we will find here in this case infinitely many lambda values. Yeah, lambda is equal to n squared. Okay. Then the other case. If we look at lambda is equal to 0, then my function x of x is equal to this. Then look at x0 is 0, that gives me c1 times 0 plus c2 is 0, that implies C2 is 0. And the other value gives me, losing the fact that C2 is 0, C1 times pi is equal to 0. C1 is 0. So I find in that case a trivial solution. So I conclude that I will find infinitely many values of lambda. Lambda is equal to n squared with n element z plus. And what kind of function do I find? Well, that are functions C2 times sine nx. Yeah, all those functions satisfy that property. Why can I leave out the constant? Yeah, so lambda n is an eigenvalue, xn is an eigenfunction. Why can I leave out the constant? Because a constant times sine x again is an eigenfunction. Think of your linear algebra, where you have also eigenvalues and eigenvectors. And if you find an eigenvector, then you know that each multiple of that eigenvector is again an eigenvector. Yeah? So we are, as mathematicians, we are too lazy to write down that constant. Yeah? We know that. Yeah? So these are my eigenfunctions, and these are my eigenvalues. Well, knowing that, so we know lambda, that means that we can also determine t. And we have to solve this equation. Substituting that equation t prime over kt is equal to minus lambda. Lambda is n squared. So we have to solve this equation for Tn. And then you'll find that Tnt is equal to a constant, let's say Tn0 times e to the power minus k times n squared times t. So we get
the square in the eigenfunction.
What?
You forgot the square. Lambda is n squared.
Oh, sorry. Yeah, you're right. Yeah, that should be a square. Here I put it again. Yeah, thank you. Yeah, so we find our eigenfunctions, we find our function t of t. Okay. So we find a solution, exponential times sine, which is a solution of the PDE and the homogeneous boundary conditions. This solution satisfies the PDE and the boundary conditions. How many solutions do we find? We find infinitely many. For each n is 1, 2, 3, etc. From this we compute the general solution. A sum over all possible solutions, Cn to the power minus k n squared t times sine nx. That's what you know already. And now we have to determine Cn. Well, and then it's simple. At t is equal to 0, you have to satisfy this. So substitute t is equal to 0. These are the initial conditions. And then you can determine the unknown Cn's. How do you do that? The sum Cn sine nx, n is 1 to infinity, is equal to fx. And how do you compute now Cn? That's by using the the fact that the eigenfunctions are orthogonal. That is an eigenfunction. Eigenfunctions are orthogonal. So what do? We multiply this expression with sine mx, n fixed, and then we integrate over the interval that we are having, because on that interval the functions are orthogonal. And if you do that, then you have to compute the sum Cn times the integral from 0 to pi sine nx times sine mx dx, n is 1 to infinity, and that's equal to the integral from 0 to pi, and then fx sine mx dx. M is fixed, n is a running variable because that's in our infinite sum. And if you look carefully, then knowing that those functions are orthogonal, their inner product will only give me contribution if this running n is equal to m. For all other values of n, they are orthogonal, so the inner product is 0. So using the orthogonality, that then leads to Cn times the integral from 0 to pi sine squared mx dx is equal to the integral of fx sine mx dx from 0 to pi. And from that you can find your Cn, which is just the inner product of f with an eigenfunction phi m divided by phi m over the inner product itself, and phi m x is just sine mx. Yeah? And that's what you learned already in an introductory course on PDEs, separation of variables. Yeah? So what you will find is actually that your solution is given by this formula, where Cn is actually given by this integral quotient. And for this simple problem, you can even compute what this integral is. What's this integral? Integral of sine squared. It's L over 2, sorry, it's pi over 2. This is pi over 2, this integral. So in between brackets, the integral from 0 to pi sine squared mx dx is just pi over 2. Yeah, if you use that, then you will find the solution uxt is equal to, well, it's over there, Cn and that's the point where actually we start with our Green's functions. Yeah, so knowing all this, so I repeated separation of variables. I could also start it immediately with this formula. Yeah, given the problem that I have, this is the solution. And what you then do is you're going to rewrite this in the following way. Introduce that constant, which is using that is 2 over pi from 0 to pi fx bar sine mx bar dx bar times e to the power minus kn squared t times sine nx. So that's my solution. I substituted just Cn into that formula. And then in the next step, I'm interchanging summation and integration. And from your elementary courses on Fourier series, you know that you can always interchange summation and integration. So I can rewrite that in the following way: the integral from 0 to pi, and then I have over here the sum of 2 over pi, and then e to the power minus k n squared t times sine nx bar times sine nx times f x bar d x bar. And what I now have, of course, is an integral representation for my solution. And that integral representation contains an integral representation. It contains my function f, and it contains something in between brackets. And that something in between brackets will turn out later to be a Green's function. This function in between brackets does not depend on f. So whatever f I choose, this will always come back in my solution. So that's the first observation. Let's consider almost the same problem, but instead of having a homogeneous PDE, we now consider a non-homogeneous PDE with the same initial conditions. So u at t is equal to 0 is f, but I only have now an additional function q in my differential equation. Those of you that did separation of variables also did the Fourier expansion method. If you want to solve a non-homogeneous problem, you expanded your solution in the eigenfunctions of the homogeneous problem. And then you're going to solve it. Yeah? To solve this problem, use the method of eigenfunction expansions. See chapter 8 in the book of Habermas. We're not going to treat that, that's what we assume that you already know, because that's the method of separation of variables. If you're going to write down your solution, it will turn out that your ux now is of course the solution that I wrote down earlier. That's the integral from 0 to pi, and then the sum 2 over pi e to the power minus k n squared t times sine nx sine nx fx dx. But I will get an additional term due to the fact that I have a non-homogeneous PDE including q. And if I do the eigenfunction expansion, then it will turn out that I can rewrite that problem in the following form: integral from 0 to t, integral from 0 to pi, and then the sum 2 over pi e to the power minus k n squared t minus t bar sine nx sine nx, and then q X bar, T bar, the X bar, the T bar. And so I can rewrite it in this way. And now if you look careful, then again you see, as in the previous integral, then we have something that is independent of my initial condition. I have here for the Q term something that's independent of Q. And what's in between brackets that looks almost similar. 2 over pi, 2 over pi, exponential, a little bit different here, but the signs are the same.
You're looking at UXX, right? The problem?
Oh, sorry. I'm going too fast. Yeah, the same problem only with a Q term. Yeah, so put also here the second order derivative. Okay. And now we define the Green's function because the solution is built up, and we define gxt dot comma x bar t bar as being that expression, the sum from n is 1 to infinity, 2 over pi times e to the power minus k n squared t minus t bar sine n x bar sine nx. And if you look careful, then all of your solutions are built up like this. Then you can continue and look at non-homogeneous boundary conditions. Yeah, because here I have still homogeneous boundary conditions. I can also take here inhomogeneous boundary conditions. And if you then write down the solution, you know from chapter 8, the book of Fredholm or whatever book, if you have non-homogeneous boundary conditions, you first make the boundary condition by means of transformation homogeneous. Then you get non-homogeneous terms in your PDE, then you solve the problem, and then again that function g turns up, but then expressing what's happening on the boundary. So in this very simple problem that you started with in the method of separation of variables, you see that your solution is completely built up what's here in between brackets. And that will turn out to be the Green's function that we're going to look for. Only for a lot of problems, we don't like that infinite series. Then we would like to have more simple expressions. And we wonder whether that's possible. Yeah, and in some cases it's possible to find nicer expressions. Is it clear for everyone so far? Yeah, so probably you are not aware of that, but already in a lot of problems you found your Green's functions. Yeah, you see that your solution is built up like that. You can read section 9.1 and 9.2 out of the book, but this is more or less what they tell you. Yeah, look at a lot of examples and see the solution is built up by all those functions G, whatever problem you're looking at. Okay, then in the book, that is section, I think 9.3. Yep, 9.3. In section 9.3 we're going to look for Green's functions for ODEs. Of course, it's not so difficult to solve this problem. Yeah? You can just iterate twice, yeah? Then you get your solution. So that's your solution which contains two constants of integration because you integrate it twice, and then you can satisfy your boundary conditions. Well, it will turn out that such problems might have a unique solution, might have no solution or might have infinitely many solutions. Yeah. The simplest way to solve this problem is integrate it once, then you get the u dx is an integral over f plus a constant, and then integrate it again. So you get a double integral. That's one way to do it. Another way to do it is, well, look at a nearby problem. Look at this problem. That looks a little bit like it. We solved it in the method of separation of variables. Yeah, I did it 10 minutes ago. So I know what my lambda values are. So I know that lambda n is n squared, n in z plus, and I know that my phi n functions are just sine and x functions. Yeah. And now let's suppose that I'm going to solve this problem in a different way. I'm going to expand my solution in those eigenfunctions. So what I'm going to do is I'm going to write down ux in the form a sum n is 1 to infinity of an times sine nx. So what I do is I expand the solution of this problem in a problem of eigenfunctions which are nearby. That these are eigenfunctions, and I just expand my solution in this way. Notice that these eigenfunctions are satisfying the boundary conditions automatically. Yeah? And I would like to solve this problem in the following way. I would like to have this eigenfunction expansion. Yeah, you can choose whatever functions you like, of course. And you can also expand your solution in the Taylor series if you wish. Yeah? But I'm doing this. Okay, so I substitute that into the problem. What do I get? The sum of minus n squared an times sine nx is equal to fx. And actually I left out a step. I can also write it down in this way. If I put over here my functions phi and x, yeah, so I do it more on an abstract level, then this term would have been n is 1 to infinity, and then I have over here an, and then phi n double prime is equal to fx. Yeah, so if I substitute the sum an phi n into my problem, then I get the second order derivative of my phi n's. That's what I write down here. Yeah? Then I know that my eigenfunction is satisfying minus lambda phi. So I will get over here the sum n is 1 to infinity of an times minus lambda n phi nx, and that should be equal to fx. Yeah? Yeah, the second order derivative is minus lambda phi. And that's what I substitute over here. And for the problem that I'm studying, I know exactly what my lambda n values are. Yeah, they are n squared. Okay. How can I determine from this equation, knowing that phi n is an eigenfunction, how can I determine the unknown coefficients an? Because in my eigenfunction expansion, I don't know these coefficients. How can I determine from that equation my phi n? My an. How do I determine an? Say it out loud. Yeah, you use again the orthogonality. So what you do, and that's exactly the same what I did earlier, you multiply here with an eigenfunction phi mx, and then you integrate over your interval. Yeah, use the orthogonality of those eigenfunctions. Okay, let's do that. I get this. These eigenfunctions are orthogonal. M is fixed. That's a fixed number. So I only will get a contribution if n is equal to m. So in the running n is going from 1 to infinity, I only will get a contribution if n is equal to m. So then I will find minus am lambda m times the integral from 0 to pi phi m squared x. The x is equal to the integral that I'm having over here. It's an eigenfunction, so this integral is never 0. So then I will get the expression, minus am lambda m is equal to the inner product of f with phi m, the short notation for the integral fx phi m. That's an inner product divided by phi m with itself. And now I see something nice. If I would like to compute am, I have to divide by lambda m. Yeah, you agree? I have to divide by lambda m. As long as lambda m is not 0, I can do that. And in the example I gave you, lambda m is equal to m squared, for m is 1, 2, 3, etc. So for that problem, I can divide by lambda m, because there is not a 0 eigenvalue. Yeah? If all lambda m are not 0, then am is just the inner product f phi m divided by phi m, and then here I have lambda m. And my solution is uniquely determined. All A I know here. Yeah, so that leads to a unique solution. Let's assume that I now have a problem for which I have an eigenvalue equal to 0. Yeah, so now the question is, what happens so let's assume that I have an eigenvalue 0. And I can give you immediately an example. If I take on both sides of my interval Neumann conditions, so I prescribe the udx is 0 on the boundary, then I will find an eigenvalue 0. Yeah? What's happening? Yeah, so for that lambda m, I have on the left hand side this expression. That means that am will be not determined. But I also have the conditional f. This inner product should be 0. So that's a conditional f. So give me your f, then compute whether that is 0 or not. If this is not 0, then this side is not 0, this is 0, then I don't have a solution because that's a contradiction. Yeah, so then I see if the inner product f phi m is not equal to 0, then no solution. And if the inner product f phi m is 0, then, yeah, how many solutions do I have? Infinitely many. Why?
Because AM is not
AM is not determined. I can choose whatever AM I would like to have, and I have infinitely many.
And this is for all m, right?
No, this is for a fixed. Let's assume there exists a lambda m. Of course, there can be more eigenvalues that give you eigenvalue 0, but usually there are only a few ones that give you eigenvalue 0. Okay. Then we have infinitely many. Solutions. And this is what we call the Fredholm alternative. Yeah? So if you don't have any eigenvalue equal to 0, then you have a unique solution. And if you have an eigenvalue equal to 0, then you have no solution or infinitely many. And that's what we call the Fredholm alternative. Yeah, so it's all run by your eigenvalues. Yeah? Okay. Oh, you're completely right. I'm going too fast. Here I have a minus sign. Here I forgot to write down a minus sign. Thank you. Yeah. Yeah, so here this minus sign is still there. Here I forgot to write it down. Okay, thank you. Okay, so it's important to see that we can solve that simple ODE by means of what is called an infinite series, an eigenfunction expansion. It's important to see that such problems such a boundary value problem can have a unique solution, can have no solution, or infinitely many. And that depends on the eigenvalues of that nearby eigenvalue problem. Yeah. If you now look at your solution, yeah, if it exists, then it's still not so nice because you have an infinite sum like this. And you all know that Fourier series like this are converging slowly. So you have to take a lot of terms to compute it. The question is, can we find a simpler expression for this infinite series? And that's what we're going to do with Green's functions. But before doing that, I have to define the Dirac delta function, and I have to define the step function. Continue with that solution. Ux is equal to, and I substitute in that solution an, and I computed an, and an was equal to minus, and I put it over there to the integral, well, like this, f phi m divided by lambda n Yeah, so the problem I would like to study is the problem with U is 0 on the boundary, so there are no eigenvalues 0. All eigenvalues are given. And then I have this. Yeah, so this is my solution. And of course I can rewrite that. I can compute this integral. That will give me in this example 2 over pi. Sorry, pi over 2, so that will give me over here 2 over pi. So I can rewrite that as an integral from 0 to pi, and then 2 over pi, the sum of, and then I will get 1 over lambda n, that is 1 over n squared, sine nx bar, sine nx times fx dx bar. Yeah, so I rewrote this, and using the fact that lambda n is equal to n squared. Yeah, and I also computed this integral, the inner product of sine squared. Yeah, that gives you pi over 2. So I divide it, then I get 2 over pi. So here nicely you also see again your Green's function. This is your Green's function, x bar. So here I have a representation for my Green's function. It's an infinite sum, not so nice, so I'm going to do something about that. Also note that this Green's function has a nice property. It's symmetric, so I can interchange x and x bar. So I have also a symmetry property. G, x bar, x. Yeah. That property will come back over and over again. And the minus sign is bothering me here. Yeah. Okay, so I now indicated that I already have 2 representations for my solution. This is one, and the other one was simply directly integrating the differential equation, and then I get a double integral over f. The question is, can we do that more nicely? But to do that, we have to introduce the Dirac delta function, and it will turn out that the Dirac delta function is actually giving me the opportunity also for PDEs to have a nice concept to compute all the Green's functions. Yeah, but first we have to define that function. Okay. Definition. Definition of a Dirac delta function. The function, it's actually not a function because it's everywhere 0 except for in one point, and the integral over that function is 1. That's the definition. And if you have a function, you usually have a function which is going from the set R into R, and R does not include minus infinity and plus infinity. And if you have a function which is going from R to R and which is everywhere 0 except for one point, then the integral over that function is always 0. Yeah? So this is a very special function. It's actually not a function, but it's a distribution. And some of you know already something of distribution theory, or not. If not, then it's also not a problem. Then you should think of the following. Keep in mind that the function looks more or less like this. here x, take here minus epsilon for instance, and here epsilon. And let the function be this, where this value is 1 over 2 epsilon. If I let epsilon tend to 0, then that function is everywhere 0, and in this case, except at the point x is 0. The integral over that function is always 1. Yeah? So if I let epsilon tend to 0, then I have a model here for the Dirac delta function. And in physics, this corresponds to, for instance, forces that are acting in a very short time interval. Yeah, with a certain amount of energy involved, or impulse involved. Yeah? So acting short time with a certain fixed amount of energy. Yeah? And this is the model. So if you keep this in mind, yeah, then you have a simple model for the Dirac delta function. Okay, that's the thing that we have to define. And then we have other thing. The heavy side or unit. Step function. We're going to look at that function. How is it defined? Well, hx minus x0 is equal to 0 for x smaller than x0, and it's 1 for x larger than x0. And if you look careful, if I compute this integral, so if I relate the heaviside function to the Dirac delta function, and I would like to compute this, what's the outcome of this integral? If x is smaller than x0, then this delta function is always 0. Yeah? And what's happening if this x here is larger than x0, then the outcome of this, the delta function, then makes a jump. So the integral will always give me a 1. So what you see here is that the heaviside function and the delta function are related to each other. And sometimes in distribution theory people write down h prime is equal to delta. Yeah, so if you differentiate this with respect to x, then you get that relationship. Yeah. So now we have seen something about a new function, and I'm going to show you that the Green's function, the nasty thing here, is actually satisfying a differential equation involving the Dirac delta function. What we saw so far is that I could write my solution in the form an integral over the interval. In this case it was the interval 0 pi, but it can be every interval, of course, that you like. Then I get the Green's function times the function that I defined in the right hand side of my differential equation, or in my initial condition, or whatever. Yeah? So this is the representation of my solution. Yeah, look here, this was the answer to the previous exercise. G times f. Yeah, I write it down here. And I was solving the equation. In this case, this example, I did this. And I had as boundary conditions u0 is u pi is equal to 0. That was the problem that I was solving. And I have this representation. I can take also another differential equation because I don't specify my g here. So if I take here another linear differential equation with f, I'm still looking for a Green's function. Yeah? Let's assume for the moment that in this problem I have here a delta function. F is a delta function. Well, let's see what happens with my solution. Then ux should be equal to the integral from 0 to pi gx x bar, and then over here I have delta x minus x0 dx. Yeah, so I take here a special function f. What's the outcome of my integral? What's the outcome of this integral? I integrate with respect to x bar. The delta function is everywhere 0 except for the point x0. Yeah, say it out loud. Yeah. Gx x0. So I see now that if I take my f in my differential equation equal to the delta function, so I put over here delta, then I will get as a solution my Green's function. Yeah. So from this it follows that my Green's function satisfies this problem. Yeah? You agree? So now I know the differential equation which my Green's function has to satisfy. So then the question is, can I solve this differential equation? And if I can solve this problem, I have a very simple representation for my Green's function. And one of the ways is of course to integrate it twice, but then you have a problem because you have here the jump. Yeah. So now we are going to try to solve this problem. And I know that I have a representation already for my Green's function, that's that infinite sum. Yeah. Now I'm going to ask myself, can I find a simpler representation for my g by solving this? Let's do that. First, let's have a look at some properties of this solution. I see that the second order derivative has some kind of singularity because it has a delta jump. So let's pose the question, the function g itself, is it continuous or does it contain a jump discontinuity? So then follow the following reasoning. Let's assume that my g itself has a jump discontinuity. That means that the first order derivative has a delta singularity and the second order derivative has a singularity of the derivative of a delta function, which is more severe than I have here. Then going back, I conclude that for an ODE, my Green's function should be continuous. Yeah, it cannot have a jump discontinuity. Yeah, so my function g should be continuous. You agree all? Yeah, because if it has a jump discontinuity, then the first order derivative is a delta discontinuity, and then the second order derivative should be more severe than a delta singularity. Or I should take the derivative of the delta function. Yeah? So g is continuous. That's what we know. Because it cannot have a jump discontinuity. Yeah, follow the reasoning, etc. Okay, that's the first observation. Okay. How do I integrate this? I would like to know g. How do I integrate this differential equation? Well, let's make life a little bit more simple. Let's consider two cases. X smaller than x0 and let's assume x larger than x0. If x is smaller than x0, then the delta function over here is 0. And just I have to solve the g dx squared is equal to 0. A very simple differential equation, which I can immediately solve because my g of x is equal to ax plus a constant b. Yeah, and I have the condition g0 is equal to 0, and that implies that my b is equal to 0. Yeah? So I then know that gx is equal to ax. And of course my x0 is in the interval 0 pi, yeah? That's always what I have. I should have a jump somewhere in the interval. Yeah? Okay. Similarly, I can do it for x larger than x0. Then also my g is equal to 0, and I know that my gx is equal to cx plus d. And I have the condition g pi is equal to 0. And if g pi is equal to 0, then I will find that g times pi plus d is equal to 0. And that implies, for instance, that my d is equal to minus c times pi, and that implies that my gx is equal to c times x minus pi. Okay. I'm still left with two constants. And this is a straight line up to x0, this is a straight line from x0. I also have the condition that g is continuous. So it should be continuous at the point x0. What does it tell us? G should be continuous at x is x0. That means that, yeah, minus pi, sorry. Yeah. So I can express A in C, but then still I have a constant. What property didn't I use so far? What property didn't I use so far? I'm solving this problem. I solve the problem for x smaller than x0, x larger than x0. There is some reason that it should be continuous, the function. But what property in this differential equation didn't I use? Delta function makes a jump, and the integral over the delta function is equal to 1. So if I integrate this differential equation near x is x0, then I can also integrate this, and I will get back the property that the integral over the delta function is 1. So what I will do is, I will integrate from x0 minus to x0 plus the second order derivative dg dx dx is equal to the integral from x0 minus to x0 plus of delta this. Yeah. This will give me 1. And if I compute this, then I get the derivative just after the jump minus the derivative before the jump. And that should be equal to 1. So what I see, there is a jump in my derivative. Yeah? You all agree? And that property I did not use so far. Okay, let's do that. Then I should compute the g dx for x0 plus. Well, what is for x0 plus? My g is given by this, and my g, the g dx is equal to c. Yeah, so this is equal to c. The g for x a little bit smaller than x0. Oh, that's ax. So the derivative is a. So c minus a is equal to 1. And now I have two equations, this one for continuity and this one for a jump in my derivative. A system of two equations with two unknowns, and you can solve it. Yeah? Okay, let's do that. So from this equation it follows that c is equal to a plus 1. And then substitute it in here and then compute a and similarly compute c. Yeah, you can do that. And then the answer will be and then the answer will be this is the answer. And why is it nice? Because I'm still have it here. That's the same representation. Here I have my G. That's an infinite sum. That nasty infinite sum is actually equal to this. And what do you prefer? This. Because here you immediately see what your G is. Over there it's hard to see, that's a triangle. Or something like this. That function. Yeah? Linear. It's hard to see from that infinite sum. Yeah, you agree? So So that's the reason why people prefer Green's functions, because the expressions are usually much simpler. Okay, looking at the time, it's exactly 10:30, and according to the schedule, we have a break, Fajar? Okay, we have a break, and then after the break, we're going to do a little bit, I give you a little bit of instruction, and then you're going to make exercises. Yeah? Question?
One small question or remark. G should be continuous at x equal to x0.
Yeah.
And we haven't defined yet what the value of G at that equal to x0.
If you take the limit for x tending to x0, then you will immediately see it's continuous over there. Yeah, because we use that fact in the, it should be continuous, you see it over here.
So we can put it.
You can put it there if you wish. Yeah, yeah, it's constructed in that way. Other questions? If not, coffee, tea break. Yeah? Oh, there. Oh, okay. Yeah. Let's move back over there. Okay, let's have a break. Okay, ladies and gentlemen, because we did not start at 9 o'clock, but at 9:15, I still have to lecture for about 15 minutes to tell you something about, well, how we can apply the Green's functions to more general differential equations. Yeah, that's what I'm going to tell you. And then after that, after those 15 minutes, I will write down on the blackboard 2 exercises. Yeah, and you can, the exercises will be something like, okay, here you have an ODE with some boundary conditions, and there are some parameters in the problem. What does the Fredholm alternative tell you? Yeah, so you have to look at the nearby problem and the eigenvalues. Yeah, so you have to look at the eigenvalues. If there's an eigenvalue 0, then there might be a problem that there might be no solution or if any. Yeah, and if there is not an eigenvalue 0, then you can have a Green solution. And then the question is, can you construct that solution? Can you compute the Green's function? Yeah, that's the idea. Yeah, so we're going to construct Green's functions, and we're going to apply the Fredholm alternative. Yeah, and then in the case where lambda is equal to 0, you will encounter a problem that you cannot compute the Green's function. And that's something we're going to discuss tomorrow. How you can construct the Green's function if there is an eigenvalue 0. Yeah, so that's what we then treat also tomorrow. Yeah? Okay. Let's have a look here. In the example, I gave you that just the second order derivative of u is equal to f. Yeah, but here I write down a differential equation, a more general second order differential equation. Yeah, and I'm going to tell you something about the Green's function. But first of all, I'm going to derive Green's formula in dimension 1. And Green's formula will give you actually the most efficient way if you have a boundary value problem with a non-homogeneous PDE and non-homogeneous boundary conditions. That Green's formula will give you immediately the solution if you know the Green's function. So you only have to construct the Green's function, and then with Green's formula you can immediately write down the solution. And that's what we're also going to do in dimensions higher. Yeah? Then we have n is 2 or R3 or whatever, Rn. Then we are going to derive Green's first and Green's second identity. And they look a little bit like what we're doing here. Yeah, so that then we're going to generalize that. And you can compare Green's formula and Green's second and first identity with the known integral theorems that you already know, perhaps Gauss divergence theorem you heard of. Yeah, that the integral over the divergence of something is equal to an integral over a surface. Yeah? And that's the Green's first and second identity are similar. What are we going to do? We are going to look at two functions u and v. And we are going to look at this expression ulv minus vlu. And I'm going to integrate it over the interval that I'm having. That can be an interval from 0 to L or from A to B, doesn't matter. And this differential operator here, in this case, is what we call self-adjoint. Yeah? So this differential operator, we have the property that L is equal to L star. Yeah, if you think of linear algebra, you also had inner products U, A, V, where these are vectors, is equal to A star U, V. Yeah, that's what you know from linear algebra. Something similar we have here, because this is also an inner product. This part is an inner product. But since the operator is self-adjoint, yeah, then you can write down this L, yeah, but actually you can also put over here an L star if you wish. Later on, if we're going to do PDEs, and we're going to look at wave equations and heat equations, then really we are going to look at L star. But this is just a starting point, and we make it during the course a little bit more difficult. Yeah, we generalize it, and then we come finally up to the answer. But here we assume that we have a self-adjoint problem. So we are looking at two functions u and v, and I write down this. And I have this differential operator. So I can rewrite this in the following way. Yeah, if I write it out, then I get this. And the ddx, so if I have here ulv, then I have the ddx with here v, that's this term, and I have q times uv. Oh, that's really q, sorry. Yeah? So I have that expression, and similarly this term vlu, then I get v times this, and I get v times qu. Obviously, this and this cancels. And then I look at this term, and this term I will integrate by parts. Yeah, so I can rewrite this as u times p times dx, in between the boundaries 0 and L, and then minus the integral from 0 to L, p times dv dx times du dx, then I only look at this term, and I integrated that by parts. I do the same thing with the other term, so I will get plus and then minus v times p times du dx, 0 and L, and then plus the integral from 0 to L, and then I have p du dx times v dx dx. Yeah? That's the first step. And then you see nicely that this integral and this integral, those cancel. Yeah. So this one and this one cancel. And then I'm left with the following: p times u dv dx minus v du dx in between 0 and L. And then I have the expression, the integral from 0 to L of ulv minus V LU dx is equal to P times U dV dx minus V U dx in between x0 and L. And this is what we call Green's formula. This is what we call Green's formula. And later on we're going to do that in R2, R3, Rn. Yeah? But actually you can say if I'm having this in a higher dimension, then this is on the boundary. And this is an interval in between 0 and L. And here I compute what is happening in the boundary. X is 0, X is L. Yeah? Let's assume that I would like to solve the problem LU is F with homogeneous or non-homogeneous boundary conditions. Yeah, that's not so important. So the homogeneous is in between brackets. And let's take for V, let's take the Green's function. So LV, in this case, is equal to the delta function. And I have that G is satisfies homogeneous boundary conditions. Yeah, so G always satisfies homogeneous boundary conditions. Yeah, so this is usually the problem I would like to solve. Yeah, with homogeneous or non-homogeneous boundary conditions. And this is my problem for my Green's function. So if I know my Green's function, yeah, then it will turn out with Green's formula that I know my solution for this problem. Because what I now do is I apply Green's formula. What does it give me? ULV. So that becomes the integral from 0 to L U L G minus G L U dx. And according to Green's formula, that is equal to the P times and then U times dg dx minus G times du dx for x is 0 up to L. What do I know? This is equal to the delta function. LU is equal to Fx. What do I know? Well, G satisfies homogeneous boundary conditions. Let's assume that here we have Dirichlet conditions. Yeah, let's assume that. And then here we have G is equal to 0 and G L x0 is equal to 0. Yeah, because G satisfies the same boundary conditions in time, but they are homogeneous. Yeah, so if I assume that I have here Dirichlet conditions, then here I also have Dirichlet conditions for G. But here they should be homogeneous and here they can be non-homogeneous. Yeah, so I can take here an alpha and from 0 or beta, whatever you like. Okay. Now I'm going to look what I have. Well, G is 0 on the boundary. Yeah, you agree, yeah? G is 0 on the boundary in this case. So that means in this example that here my G is 0. The G dx is not 0. So I can rewrite this in the following way. U times the delta function, integrated with respect to x. What will give me that first term? U is 0. Yeah, so the solution in the point x0. What will give me the other thing? Well, that will be minus an integral from 0 to L, G, x, x0, fx, dx. Yeah, you agree? L, U is f, and here I have just my Green's function, and I integrate with respect to x. Is equal to. Okay, then I have to substitute the upper bound, and I will get PL times U in L times the G dx in L x0. Yeah? Minus the lower bound, P0 times U0 times the G dx in the point 0, x0. Well, in this example I specified U0 is alpha, so this is equal to alpha, and in this case UL is 0. So if I now would like to know the solution in the point x0, then that solution is equal to this integral plus, well, this is 0, plus this, where I have to compute the G dx. Yeah, I did not specify now a differential equation, so I don't know what G is, but I can compute it. Yeah, in the first example before the break, I computed it. So if I know G, so if I can solve this problem, then I only have to apply Green's formula, and I only have to substitute G and what my functions are on the boundary and what my f is. And then I have completely my solution in a certain point x0. So once you have solved this, then whatever problem you have for U with homogeneous or non-homogeneous PDEs or boundary conditions, you can immediately write down Green's formula and you have your answer. So that's the reason why people are so interested in Green's function, because if you have the Green's function, then you immediately have the solution of all the problems that are nearby. Yeah? So by solving one problem, you automatically have all solutions. And that's also what we're going to do the coming week for higher dimensions. But then the difficulty is how to compute such Green's functions. Yeah, so then we have to do a lot of work in computing it. Yeah, and don't forget, what we are presenting to you was 100 years ago, was pure research. Yeah, that was high level. And people discovered that. Yeah, so what I'm telling you, which seems trivial, was not trivial 100 years ago. It was research. Yeah, and what we now do for research, we think it's very difficult, but over 100 years a lot of people will say, oh, that's trivial, because of this theory. Yeah? Okay. This is clear for everyone? And now you see the purpose of constructing those Green's functions. Solve one problem, then you know the solutions of all the problems. Okay, now I have a few exercises for you. And then you can work on until the break and I walk around, so if you have questions then I can answer it. And those exercises are the following. This is the first exercise. So it's just a second order differential equation. Yeah, there's not so much difference as in the first example. I added here a linear term. And instead of fx, I explicitly give you e to the power x. Yeah, so I just give you the function fx. I also define that on an interval of length L, and L is not yet determined. And the first question is, if you look at the eigenfunction expansions and the eigenvalues of a nearby problem, what does Fredholm's alternative tell us about the solution? Is it unique? Is there no solution? Or are there infinitely many? Yeah. Then the question is, try to construct Green's function. And then, with using the Green's formula, determine ux. And I will put a similar example question on this side of the blackboard, but then with another second order differential equation. Yeah, with the same questions. Yeah, so you can now start with this exercise. So I continue over there. Then you will find that your phi of x is equal to c1 cosine and then square root of 2 times x plus c2 sine square root of 2 times x. I saw the solution, a few of you, well, I saw it a few times that people found this solution. And now you have to look whether this is a trivial solution or not. So if C1 and C2 are both 0, then I have only the trivial solution, so lambda is 0 is not an eigenvalue. Okay, let's look if that's possible. Phi 0 is equal to 0. That means that C1 is equal to 0. Yeah? Then we look at phi L is equal to 0. And that implies that C2 times the sine of the square root of 2 times L should be 0. Well, two possibilities. C2 is equal to 0, or the square root of 2 times L is equal to n pi, with n elements set plus. Yeah? Well, if C2 is 0, then because C1 is 0, then we have the trivial solution. So I will not consider this case. Yeah, that gives me the trivial solution. So if the square root of the square root of 2 times L is equal to n pi, then I have an eigenvalue 0. So it now depends on the length of my interval. If the length of my interval is equal to n pi over the square root of 2 for a certain n, then I have an eigenvalue 0. So the conclusion I can draw is, if, I better write it here, if L is not equal to n pi over the square root of 2, then we have a unique solution. Yeah? If L is equal to n pi over the square root of 2 for a certain n in Z plus, yeah, then I have to rethink again, because then I have two possibilities, no solution or infinitely many. And in that case I have to look at what kind of integral I have to look at. Yeah, I have the eigenfunction expansion. You're computing an minus an times lambda m is equal to the inner product of f with phi m divided by phi m with itself, the inner product. Yeah, you remember that? So then I have to look at the inner product of, in this case, e to the power x with phi n x, whether that is 0 or not. Yeah, if this inner product is 0, then infinitely many solutions. If the inner product of that phi n for which L is equal to that is not equal to 0, then no solution. Yeah? So now you have to compute. Well, if you say I have this, then I have a unique solution, and then you can continue with the next part, construct G. Yeah? And then later use Green's formula to construct U. Okay. If you're in this case, and you're in the first case, then you know that you have a non-unique solution, you have infinitely many. That's what I'm going to explain to you, how to construct a Green function for those problems. I will do that tomorrow afternoon. But for the first case you can construct it. And also the last conclusion you can immediately draw. If this integral is never equal to 0, then I have no solution. And if you compute this integral, it turns out that you are in this case. So if L is equal to n pi over the square root of 2, then you are in this case, so then there is no solution. So this exercise will not force you to do this. Yeah, so if you compute this integral, it will turn out that you're here. Yeah? Okay, continue with this exercise. This problem is almost similar, but there is an eigenvalue lambda is equal to 0. If you look from the physics of the problem, you will understand what's going on. Because what you have over here and over there is in fact you have a rod. And what you do, you take the temperature here equal to 0 and you take the temperature here equal to 0. This is at x is 0, this is at x is L. This is coming from a heat equation, and actually you're looking at a stationary solution, so a time-independent solution. Yeah? This term is the diffusive term, and this term is a radiation term. So heat is radiated proportional to U, the temperature over there. And what is this term? This term is energy production within the rod. Yeah? Similarly here, radiation, production. And if there is a balance in between radiation and production, then you can have a solution. Similarly here. For this example, it will turn out that in most cases you will have a unique solution, and if you're in this case, there will be no solution. This exercise is made in the following way. If you will do the exercise, it will turn out that lambda is 0 is an eigenvalue. And then for most beta values there is no solution, and there is only one beta value for which you have infinitely many solutions. So in those two exercises you see all the possibilities of the Fredholm alternative. So try to make this exercise continue until it will continue until lunch until 12. But also try to make it, if you have time today, to finish those two exercises. And tomorrow I will go explicitly to the exercise where we have an eigenvalue 0, how you then construct G. Because then we are talking about generalized fixed functions. And it does not matter whether we are working in a one-dimensional space, it also in 2 dimensions and 3 dimensions we get similar things. Only the concepts are the same, only the problems are more difficult because we have really